Okay, so here we go. We are going to be talking about inclined planes and a lab that maybe you'll do today, maybe you won't. But look at all these nice colors here, blue and green. You guys know your colors, right? Okay, so anyway, we are going to be working first on an inclined plane practice problem. And then we will kind of go from there and talk specifically about the lab. So that way we understand, maybe like as a little review, like what is exactly going on. And then we can apply that to the lab so that we can be ready for a test on like Thursday, Friday region. So here we go. So inclined plane. So we have this down here. This guy's super excited about it. He's going to eat it. And he's just as excited as you are. All right. So here is kind of where we're starting with these problems. Where you're given a block on a plane and an angle. This is the most general and most basic. There are lots of different examples that we can have, even just from this setup. One particularly, it's particular in the way that people often get it wrong because they forget what it means. And I think some of you fell into this trap on the quiz on Friday. And that is that if velocity is constant, that means something. And that means something very specific. And that really, what it means is the thing is in equilibrium. And equilibrium has some really important attributes that go along with it. All right, so that means when an object is in equilibrium, that namely means that the F net is equal to 0 newtons. So when we have a constant velocity, if we want to work actually, from this idea of a constant velocity, an idea of constant velocity means that the net acceleration, the A net, is equal to 0 meters per second squared, which in turn means that the F net is equal to 0 newtons because we know that F net is always equal to ma net, and hopefully that's not totally cut off. All right, so we know that these two things. This ultimately means that the forces are balanced. All right, so when the forces are balanced, that tells us something as well. I nearly spelled it correctly. You're welcome. So that means that no matter what we've got going on, the forces up and the forces down, they're all going to balance out. So they don't have to be pointing exactly in the same direction, but they're all going to balance out. So let me give you kind of an example up here. So if this situation right here, if this block on this plane, so different than the one that maybe we were just looking at, even though we haven't put any numbers on it, if I were to tell you that this block, right, was traveling at a constant speed, okay, that the speed was constant speed, right, and I could say constant velocity or constant speed. It doesn't particularly matter. Or if I said any of those other attributes, like the forces are balanced, or the acceleration is 0, or even that it's held at rest. That means that even though these are the only three vectors acting on it, right, the force of gravity, the normal force, and the force of friction, it means that when we put them together, they are all balanced out. Sort of like that problem from your homework last week that some of you did, some of you didn't. The review book problem where you had three vectors that you had to line up and say, like, well, what is the resultant of the other two? And the three vectors were an 8 Newton vector, a 6 Newton vector, and a 10 Newton vector. Now, no matter how we line up these vectors here, when you put any two of them together, they have to be equal and opposite to the third. Meaning, like if you only had this 10 Newton vector pointing in this direction, very similar to this one, well, how would you cancel it out? Well, the only way to cancel it out would be another 10 Newton vector pointing in the opposite direction, right? The exact opposite direction with the same magnitude, right? So that this angle right here would be 180 degrees. Okay, so that tells us that the resultant, okay, of the 8 Newton vector and the 6 Newton vector has to be 10 newtons, right, and exactly opposite of this. So whatever angle these are at, we don't know, we're not specifying in this case, but we know that the resultant of the 8 and the 6 has to be the same as saying a 10 Newton in the opposite direction, right? So that when we put them together, that we are able to say, well, these two things have to be the same because it have to cancel out this. Likewise, if we put the 10 and the 6 together, it has to be exactly 8 newtons and exactly opposite this 8 Newton vector. And again, this is all if this is in equilibrium, right? This is the idea that this system is in equilibrium, right? If it wasn't in equilibrium, these things wouldn't have to be true. But all these forces have to balance out because we're saying that it's in equilibrium. And that also means that this 6 Newton vector has to cancel out with this other 6 Newton vector when we put the 8 and the 10 together. Okay, so hopefully that makes sense. But so we get rid of all this, and again we say that this thing is traveling at a constant speed, and this is a really typical problem that we'll see on the Regents, we'll see on multiple choices, and obviously you'll see on your test. And so what this comes down to is the fact that whatever the forces are here, they have to cancel out in that similar situation. You notice the picture is very similar to the one I just drew. But we have this ramp here that, for whatever reason, we feel like complicates it. All right. When we did these problems before, we rotated our coordinate system. And when we rotated our coordinate system, we called this right here, all right, this direction here, we said that this was our new x direction. All right, and then we said this direction, we said this direction right here, this was our new y direction, right? And I know I said I wasn't going to call it new x and new y anymore, but it's helpful here as we kind of get going again. Those two directions there are important because, and we chose them because in our x direction now, this is the only plane of motion now, meaning that this block here is going to slide down the ramp in the x direction. So we don't have to worry about the y direction at all. It totally cancels out. It's maybe not obvious why it cancels out here, because if you look at it right now, we just have one force in the y direction. Well, that's because our FG right here is neither in the x nor the y. And just like when we had, a block on a plane, we did lots of examples like this, right? You have a block on a plane, you pull it up at some angle. Well, this is not in the x or the y direction, right? And if we were to draw in our coordinates, just like we are right here, we would see that this x direction is the only plane of motion, right? Even though we're pulling up on this, we're saying right now that we're not pulling up enough to lift it. And so in order for us to talk about how it moves, we only have to talk about the x direction. Everything in the up and down direction cancels out. So what we did before was we did a little bit of work, and we said, well, because we know this angle, that means we can do a little bit of trig, and we can figure out each of these two sides. And this is going to be some force in the x direction, and this would be some force in the y direction. And while the y direction is going to affect what happens with the normal force, we ultimately knew that the sum of the forces in the x direction was going to be equal to the net force, right? Just the forces in the x directions were the ones that mattered, because we weren't lifting it up. And that worked for us, and so we were moving along pretty well with that. We added friction, and that complicated things a little bit, but in the same sense, we understand that we need to find the components of this force here. All right, so in looking for the components of this force here, we can see that we have a certain amount in this direction. That is pretty large. I guess I should go here, maybe there. So we have a certain amount in this direction and a certain amount in this direction. And we spoke earlier, and I'll do it again in a second, but ultimately this is the component here. This is the part of gravity in our x direction. Right? This is the part of gravity in our y direction, because our coordinate system now looks like this. By definition, these two things are always going to be perpendicular to each other, right? These two. This has to be a right angle. And we spoke that because we rotated our coordinate system from where the FG was, that this angle right here was the same as this angle over here. So now we have this right triangle here, and we could do trig. Now, I'm not doing it right now. We'll do the example problem here, but this is just kind of laying out one of the types of problems that you could see. So ultimately, what does all of this mean? That means that this component down here, the FGX, is the only one that we really care about, because just like before, we know that the sum of the forces in the x direction have to equal the F net. We know that because the y direction is going to cancel out. We know that because it's moving along this surface. It's not leaving the surface. It's not melting into the surface. It's just moving along the surface, which means all the forces in the y direction, just like they have been for a while now, are going to be zero, right? Whenever you're on a surface. All right, the forces in the y direction cancel out. So if this question is telling you that this thing is traveling at a constant speed, that means the force down the ramp, okay, and the force up the ramp have to be equal to each other. So this ultimately means, well, there's only two forces. This force is down the ramp. This force is up the ramp. So we can rewrite those forces, all right, in here. Whoa. We can rewrite those forces in here, and we can say that the sum of the forces in the x direction, well, what are they? Well, it's FGX, okay, and it's FF. Those two forces, when you put them together, have to be equal to the net force, okay? But we know something, that when we say constant speed, we know that the net force is equal to 0 newtons, because constant speed means equilibrium. So when we write these two things out and we say this plus this has to equal 0, and one is going in one direction and one is going in the other direction, we know, and the algebra tells us as well, that those two things have to be equal in magnitude, so the numbers have to be equal but opposite in direction. Okay, so whatever the numbers are. So if you're told what the force of friction is, then you know what FGX is. If you're not told what the force of friction is, then you can find the force of friction just by finding the FGX. So people often struggle in a question like this because they say, well, they didn't tell me what the mu was. They didn't tell me what the coefficient of friction was. And the question is maybe asking you, what is the force of friction equal? Right? I'll give you this whole problem to say a block rests on a plane, an angle, whatever. What's the force of friction? Right? And so this is the question you're being asked, and so immediately a lot of you are going to say, well, the force of friction is equal to mu Fn, but I'm not told this. So how can I find this? All right, this is how, right? This is how we did it. We said we need to figure out the force down the ramp, because we know that the forces are balanced, so the force up the ramp has to be the same thing. Okay, so again, they're just like when we were talking about the net force. There's more than one way to find the net force. Right? We can either find it by this method, by saying it's on a ramp, and or it's moving along a surface, so the forces are just whatever they are in this direction, or we could find it by saying, well, F equals ma, right? And if I know an acceleration, I can figure out a force. The force of friction is a similar way, because we have a separate equation to find it. We don't necessarily have to use that separate equation. We could just know some of the other forces. This also doesn't have to be a friction problem. Instead of saying friction up here, we could also say that this is some force applied instead. Some force Fa. So, and they say that this force maybe keeps it at a constant speed, or they could say that it's held at rest. Either way, it means it's an equilibrium, and nothing really is going to change about what we do. We're still saying it's a constant speed. We're still saying that the sum of the forces in the y direction is 0. We're still saying that the net force is equal to the sum of the forces in the x direction. And then all we're going to do is change this from a force of friction to a force applied. And we are still saying that whatever that force is going to be equal to the FGX, because it's an equilibrium. All right, so equilibrium tells us that the forces are balanced. Okay, and sometimes we're just going to have to do a little bit of trig to figure out what that other force is. Okay, so let's take a look at a problem with numbers, and back to this this happy guy here. So when we're looking at problems like this, and this guy's distracting, so let's get rid of him. Let me get rid of some of this stuff. When we're looking at problems like this, and we actually have to do some calculations, you might find once you kind of get over the drawing of the pictures and stuff, that it's really not too bad, and that you actually maybe even prefer these to those blocks on a plane at some angle. And the reason is that some of these things ultimately become pretty straightforward, and you can get in a pretty good routine as you begin to go through these. So here is our new coordinate system. This should always be your first step so that you can make sense of the world sort of that you're living in now, meaning like how you are looking at this problem. The coordinate system is what's going to tell us what we need to do, and we choose this coordinate system because it makes it easier for us. This x direction here is useful for us, and this y direction here is useful for us because the x direction is now parallel to the direction of motion, and the y direction is perpendicular, and all of the motion is going to be in this x direction. We couldn't have used this method with, say, a projectile motion, because in projectile motion, it doesn't move in a straight line. We're able to use this trick here because this block is moving in a straight line. If we didn't rotate this coordinate system, this would be moving in 2 dimensions, and it would sort of just be a pain. Okay, so once we have this drawn in, our next step should really be to draw in our vectors. So I'm going to first draw in my force of gravity here. And the force of gravity always pulls everything straight down. So not in this y direction that I have drawn here, but straight down. All right, so there's my force of gravity. I'd say that this is a 100 Newton block, so that 100 newtons is the Fg. I'm not sure how well that shows up. So normally we would say Fg is equal to mg. We don't need to do that here because I'm telling you a number that is in newtons. That means that is the weight of that object. Right? Fg is weight. And it says that on your reference table, so you can just use that. So what else do we know? We also know that the normal force is always perpendicular to the plane. It's equal and opposite to the force applied to the plane, and it's perpendicular to the plane. Okay, there is going to be friction in this problem. I'm not going to look up, have you look up a mu, but I could say something like this is steel on steel, or wax ski on snow, or something like that. But I'm just going to kind of keep the math pretty straightforward here, and I'm just going to say this is a mu of 0.1. Again, there's no units on there, but that is the coefficient of friction that we're using. And that's what we'll kind of move forward with. So because we know that the friction is going to be present, and it's going to be acting up the ramp, and it's going to be, again, parallel to the ramp because the block is moving parallel to the ramp. The force of friction is always parallel to the direction of motion. So this would be the free body diagram right now. Free body diagram does not include the components. It only includes the forces that are really there. The components that we use, meaning the FGX and the FGY, are just there for us to kind of make sense of it. They're tools for us. They don't exist in the world. Even though we always end up drawing them, they're just not part of the free body diagram. That's just the rules. So let's say that this problem is asking us to find the net force. Okay, so we're just saying what is the net force. So we move on. All right, we take we got our free body diagram drawn, and that's really, really important. One of the ways that I kind of the methods that I sort of taught you in class was we want to draw a guideline. We want to draw a line that is parallel to our x-axis, parallel to the ramp, and these two things are parallel to each other. So we want to draw a line sort of like this, And you can use a straight edge or something like that to help you out with it. But the purpose of that line is so that it's kind of like dropping a vertical like we did before, so that you are drawing this triangle the way that you are supposed to be drawing it. So when we draw our components, we have the two pieces of this FG that are in or parallel to our two directions of motion, our perpendicular and our parallel direction. So now I need these vectors to be the same as my FG, in that they have to ultimately do the same thing. So this FGY is the part of gravity that is parallel to my y direction. It's actually just in my y direction. It is perpendicular to the motion. All right, and this is my FGX. This is the part of gravity that is in my x direction. These two things, these two red vectors here, make up my FG. So once I have the values of these two vectors, I don't need this FG anymore. I won't use this 100 newtons for anything other than finding my FGX and my FGY. Right. We talked about this before, but just so you sort of remember here, these two angles are always going to be the same because we rotated it. So that angle of 30 right there is that angle there. So now we have to do just a little bit of trig. We have two equations that we'll mostly use, and you really shouldn't have memorized that sine goes with one and cosine goes with the other. So I'm going to do just a little bit of that work below here, and then we'll scroll back, I guess. All right, so if I pull this down just a little bit, I can say, well, I know that sine of theta is equal to the opposite side over the hypotenuse, and I know that the cosine of theta is equal to the adjacent side over the hypotenuse. I can substitute in those values. The sine of 30 goes here. Well, the side opposite this angle, right? So here's the angle, and here's the FGX, right? Those are the sides opposite. I guess I
label them. This is the angle we're talking about. So this is the opposite side. This is the angle we're talking about. So this is the adjacent side. This is the triangle, the right triangle we're talking about, right? So this is the hypotenuse. And we already said up here that the FG is 100 newtons. So the hypotenuse of this triangle is 100 newtons. Okay, so we're going to find other sides here. All right. So back to this map, the opposite side, because we just labeled it, is my FGX, my hypotenuse, is my 100 newtons. Likewise, I can finish this up, sine of 30 is a half. Right, so using some algebra and some trig, we're going to say that the FGX is 50 newtons. This becomes the cosine of 30 degrees is going to be equal to my adjacent side, which is my FGY, over my hypotenuse, which I labeled from up there, which is 100 newtons. So that's cosine of 30 is about 0.866, so we'll just call that 0.87, which means when I do my algebra, I'm going to say my FGY is equal to 87 newtons.
Okay. So, now when we look back at this business, and I'll give myself a little bit of room to work over here, we can start to fill in just a little bit more of this. Hopefully that shows up. So now I know that my FGY, okay, is equal to 87 newtons, and my FGX is equal to 50 newtons. In terms of the forces that are acting on the surface right now, right, are acting in these dimensions, I know that the sum of the forces in the x direction, that there are two, okay? Just like in the other example, there is FGX, all right, and there is the force of friction. As far as the y direction is concerned, there are two as well. The sum of the forces in the y direction, there is the Fn, right, the normal force, not the natural force. There's no such thing. And the FGY. We had some rules before, and the rules were two of them were that the sum of the forces in the y direction is equal to 0 when it's moving along a surface, and the sum of the forces in the x direction are equal to the net force when it's moving along a surface. So we can say those things here as well. So now we can say that this is equal to the net force, and we can say that this right here is going to be equal to 0. All right, get rid of that. this right here is going to be equal to 0. Very good 0. All right, now what? All right, so now we can start to think about some of these numbers, right? We could put in some numbers here. Like, for example, I know that this is 50 newtons, but I don't know what my force of friction is yet because I'm going to have to do some calculation up here. I know that my force of friction is equal to mu times my normal force. Well, since there are only two forces in the y direction, and we've said this before as well, we know that my force of gravity, what is going on there? My force of gravity in the y direction is going to be equal to my normal force. It's getting a little crowded. So because I know that my force of gravity in the y direction right here is equal to 87, that means that that is also equal to my normal force. The force of friction is going to be equal to that 0.1 that we said it was before. The 0.1 is my mu times my normal force, which we said is 87 newtons. So pretty easy math right there. The force of friction is going to be equal to just 8.7. Okay. So now we can bring that information up here. Now we know that this is equal to 8.7 newtons, and then my net force is going to be that right there. Well, we have to be pretty careful here because we have these right here as just adding together, which is not the case. They are pointing in opposite directions. The force of gravity in the x direction is pointing down the ramp. The force of friction is pointing up the ramp. So one of those definitely has to be negative. Okay, so carrying this over right here, I'm going to instead say that this is 50 newtons minus 8.7 newtons, and that is going to be equal to my net force. Right, so a lot of math here, just a lot of stuff just to get to what our net force is. So our net force is then going to be equal to, what is it, 51.3 newtons. What? Excuse me. 41.3 newtons. Hashtag math. Okay, so that's our answer. So when you look back at all the things that we did here, just for this one problem, we had to draw this gigantic picture, and we had to make sure we drew it correctly so we could do our trig correctly. Then we had to come down here, right, and do our trig. But really, when you look at all these crazy formulas and all these forces with all these subscripts, what it comes down to are really just addition and subtraction, right? There are two forces in the y direction. They cancel out. We need to know that they cancel out so that we can find this normal force. After finding that normal force, we can substitute it into this equation, and after substituting into this equation, we can figure out what the force of friction is. We can use that force of friction in our y direction because that's where it works. All right? Excuse me. We can use that force of friction in our x direction because that's where that works. And then we had to remember that the force of friction opposes the direction of motion, right? So we had that. We couldn't just add them together, right? Because that would give us the wrong answer. That would say the friction was helping it move, but it's slowing it down. So we get that our net force is less than it would have otherwise been if there was no friction, which is again another way for you to sort of check that. All right. So continuing on here, this is getting to be pretty lengthy. And I know I started the video by saying that we were going to be going over the lab, but I think that's maybe enough for today, so it gets you a little refresher on inclined planes. Now we can start to work on some review stuff for the test that we'll have either Thursday or Friday of this week. So have a good weekend. Just kidding. See you tomorrow. Hopefully.